Introduction to torque. I will introduce torque first by talking about equilibrium. How do we know if an object is in equilibrium? When talking about equilibrium, the first thing that comes to my mind is balance. So, when an object is balanced with another object, you put it on a scale, both objects you put on a scale, then the scale will stop moving. So, an object is not moving. Is that the only instance of equilibrium for an object? Is it possible for an object to be moving but also in equilibrium? Well, the correct answer is yes, it is possible for an object to be in equilibrium even if it is moving. There will be some state of balance even if the object is moving. For an object that is not moving, it's a little bit more obvious that there is a state of balance, but it's probably less obvious for an object to be moving and still be in balance. But if you've ever been inside a train, not a train, an airplane, if you've ever been inside an airplane, there will be instances when you'll be soaring through the clouds, flying through the clouds, and sometimes it feels as if the plane is not moving. But it is actually. Sometimes the flight can be so smooth that you can just, if you close the windows, there would be no way of knowing that the plane is actually moving. But when the turbulence hits, then that's the time you realize, oops, I just hit the clouds. But that is a state of equilibrium. The airplane is moving at constant velocity. So it's really more to do with acceleration than not moving or moving. So an object is in equilibrium if it is not accelerating. So that means that its linear acceleration is zero. But since we've been talking about rotational motion, we add the other condition that the angular acceleration is also zero. In an omega versus time graph, that will look like this. For an omega versus time graph, it has to be a flat line. So maybe 5. So maybe your omega function of time is 5 radians per second. Now, if you get the angular acceleration, you get the differential of omega t. And what is the differential of a constant? You'll get the derivation of 5, and you'll get 0. The steepness is 0. This is an example of zero acceleration. This is an example of equilibrium. An object is in equilibrium if it is not accelerating. 0. So when an object is not moving, it has what is called static equilibrium. When an object is moving but with constant velocity, that is referred to as dynamic equilibrium. So static equilibrium velocity is 0 from the perspective of a person looking at the object as a frame of from the reference frame of an object looking at the object. It's not moving, 0 ang iyang velocity. This could be angular or linear velocity, and the person can conclude that the object is in static equilibrium. Now, from the perspective of a person, if the velocity is constant, moving past him but at a constant velocity, or rotating around the axis at a constant angular velocity, then that object is in dynamic equilibrium. Yeah, as I mentioned, there are two kinds of acceleration and both must be 0. Recall that for linear acceleration to be 0, the sum of all forces acting on an object must be 0. I hope you still remember Newton's second law of motion. The sum of all forces, this is the vector sum of all forces acting on an object. Forces may include gravitational force, a pushing force, normal force, tension force. If you add all these forces up vectorially, vector addition, and that if it equates to a value, then that value has something to do with the mass of the object and the acceleration of the object. Now, if the object is in equilibrium, your acceleration is equal to zero. So the whole expression here on the right side is zero. So you say that the sum of all forces is equal to zero. This is condition number one for equilibrium. For equilibrium. Condition number one for equilibrium, that the sum of all forces acting on an object must be zero. For example, if you have a book on a table, the book, now there are two forces acting on this book. You have the gravitational force, and if you remember, the normal force. When you're adding all these forces vectorially, you'll find that the normal force has the same magnitude as the gravitational force. The only difference is their direction. So if we assign upward to be positive, your normal force is positive, your gravitational force is negative. So when you add those two, the answer is zero. Here, the sum of all forces is zero, which implies that your acceleration is zero, which implies that this book is in equilibrium. And what type of equilibrium? Static equilibrium. Now, for angular acceleration to be zero, the sum of all torques acting on an object must be zero. So torque is the equivalent of the rotational equivalent of force, but it's a little bit different from force, which we will figure out. We'll learn later what their difference is. But for angular acceleration to be zero, the sum of all torques must be zero. And here is Newton's second law in rotational form. So see the similarities? Instead though of force, we write torque. Instead of mass, we write, you know this, the rotational inertia. Instead of linear acceleration, we write angular acceleration. But if we want the object to be in rotational equilibrium or in equilibrium, then our angular acceleration must be zero. So this is actually the second condition for equilibrium, that the sum of all torques must be zero. But I've been talking about torque, but I haven't introduced what torque is yet. So the next slide will introduce us to what torque is. What causes rotation? Now, the answer is torque. Torque is something that produces or attempts to produce a rotation. Torque is what causes an object to acquire angular acceleration. Consider this figure of a pulley, and there's a force acting down on the outer edge of the pulley. Maybe it's a string, causing the pulley to rotate. Imagine sa sugod, wala pa na force. So initially, the pulley has zero angular velocity. But when the force was applied, finally we have maybe, I don't know, 2 radians per second. So there is an acceleration, right? So the force caused the angular acceleration. So we now established that the force is an important component of torque. It's not, force is not torque, force is just a part of torque. Because it takes more than a force to make an object rotate. You have to make sure that this force is causing rotation. Because there is a way to apply this force, this same exact force, but it cannot make the object rotate. There are several ways to do that. Here's one way to do that. What if you apply this exact same force in that manner? Imagine that pulley will never rotate because you're pulling to the left. You're not causing the object to rotate. Or imagine if you're applying the force in this direction. you're actually applying the force downwards, but the pulley will still not rotate because you're applying the force on the axis. You don't want to do that. So there's definitely more to force than just the to torque than just the force. Torque is more than just the force. In fact, a force can create a torque, but not always. It can only create a torque if it is applied some distance away from the point of rotation. It has to be some distance away from the point of rotation, so that's why this doesn't work. If you apply a force on the axis, that's not a distance away, that's on the point of rotation, and that will never rotate. The second is at least a component of the force must be perpendicular. So you can probably apply a force like this, and that's okay. That pulley will rotate, even if it's not fully straight down, because at least a component of this force is straight down. This example I gave earlier, wherein the force is to the left, that doesn't have a component pointing down. That will never cause this pulley to rotate. Okay, so these are the two considerations. Your force must be some distance away from the point of rotation, and at least one component has to be perpendicular to the force. We'll look at this formula later. So let's consider this situation. Oh, I'm sweaty. Now, O is the axis of rotation, and F is the force that you apply. Question is, will this object rotate? It looks like it will, but I'm going to focus on this formula. What is this formula? What is this R sub perpendicular? This is one formula you can use to solve for torque. As you can see, it has the force component in there because of force. It's really a crucial part of torque. If you know the magnitude of the force, you need to know one other variable which is also important, and that is this R perpendicular some sort of thing. And to get R perpendicular, to know what that is, first thing you need to do is to draw this sort of dashed line, and it's called the line of action of the force. You have to do that. That is important in knowing what R perpendicular is. And as it turns out, R perpendicular is this line, and it's called the moment arm. And the moment arm is R perpendicular. The moment arm is that distance from the axis of rotation to the line of action of the force, wherein the moment arm is perpendicular to that line of action of force. So if you can somehow find a way to get R perpendicular, and as you can measure this, it has to be perpendicular to the line of action of the force. And if you get R perpendicular and F, and you multiply both, you get the torque. This is another important R. This is different from R perpendicular. This is known as the position vector for the point of application for the force. The difference is that R, this is the position vector, and R perpendicular, that is the moment arm. Those are two different things, but you'll find out later they are related somehow. So the difference is R vector is the position vector. It's the distance plus direction of from starting from the origin or the axis of rotation to the point of application of the force. You can see that R perpendicular and R vector are related actually. Actually, R perpendicular is the perpendicular the one of the components of R vector. Okay, this is R parallel, but this is not really important to us right now. They are related. Okay, let's first dive into the concepts of torque. Which of the following would create a larger torque? FA or FB? So let's draw the lines of action. This is a hinge. This is an overview of a door, top view of a door. And let's draw the moment arm. So it's really hard to draw a straight line, but I'll try. This one is, oops, sorry. This is R perpendicular for A, and the other one is R. Okay, good. R perpendicular for B. Now let's calculate the torque. So the torque of A is R perpendicular A, FA. This is the moment arm times the force. Torque B is R perpendicular B, FB. Now, what is the difference between the two torques? Apparently, they have the same forces because the length of the arms are the same, but they differ in the moment arm. Which moment arm is bigger? R perpendicular B is bigger. It has a bigger moment arm. So therefore, it's a larger moment arm. Therefore, um, force B creates the larger torque. And how would we know that? This is exactly the reason why doorknobs are located as far away from the hinge as possible, because you need only a little amount of force to cause a torque if you put the doorknob here. If you put the doorknob here, for the same amount of force, you will be creating less torque and therefore less acceleration. So you need to add more force here to match what FB can do. So it's not practical to put the doorknob here in the middle of the door. How much more if you put the doorknob here on the hinge? So you will never have the ability to open that door. How about if you put the doorknob here? If you apply that force, well, that door will never rotate. Anyway, how about this? Which of the following would create a larger torque? For this particular example, we use the second way of measuring torque, which is that this time we involve the position vector, r, and the force, and the sine of theta. That is the short angle between the position vector and the force. So if I haven't emphasized it enough, there are two ways to measure torque. This is the first formula, which involves the moment arm, and this is the second formula which involves the position vector. And I'm gonna draw the position vector. It's from the hinge to the force, right? Okay, this is position vector A, and apparently position vector A and position vector B are the same length. So let's position vector A, magnitude of position vector A, magnitude of force A, and this is where both forces differ, like the short angle between R and F. Let's do that. Okay, let's figure out what the short angle is. First is we draw RA. And then we draw FA, and we do that in such a way that their two tails meet. That's how you determine the short angle. And I'm just gonna estimate here because I don't have values, but I'm just gonna probably, it looks like it could be 30 degrees. That's probably a wrong estimate. And let's check out torque B. RB, FB. And now let's determine the short angle between RB and FB. So let's draw RB, pointing to the right, and FB. Let's join their tails. Yes. Okay. Now the short angle is 90 degrees. So let's put 90. So we know that RA, the magnitude of RA and RB are the same. Magnitude of the forces are the same. Where they differ is the angle. Sine 30 is 1 half and sine 90 is 1. So which do you think is the bigger torque? Apparently, the force B produces the larger torque because sine 90 is 1. And force A produces only half the torque of torque B. And it makes sense, right? Imagine if you're the one pushing this door. You would you wouldn't want to push at an angle. You want to push perpendicular to the door. Okay. Okay, I'm gonna stop here and make another video for the problems. Thank you.